Okay, so Benedikt Ahrens is going to tell us about categorical structures for type theory and univalent foundations.
Thank you. Thanks a lot. So this is about joint work with Peter Lamstein and Vladimir. The overall goal of this project is to compare the various categorical notions that are used in the study, the mathematical study of type theories. So for instance, C-systems, categorical families, the type categories, categorical maps, and so on. Well, by constructing maps between them and proving properties of these maps. This project is not so much about models of type theory. So often these gadgets are used to interpret syntax, and then we want to consider additional structure on these gadgets, but I will not talk in this talk about this additional structure. So the first question that is important is how do we compare different definitions? So in an agnostic setting, or if I want to be more specific, in set theory or in plain type theory, the structures that we're looking at would be needed to compare on. We would need to compare them on the level of, say, categories or bicategories or something, meaning that we would have to consider the notion of isomorphism or equivalence between these structures. In univalent type theory, we can do without a notion of morphism of these structures, because the notion of identity will encapsulate exactly the right notion of sameness. Good. So more specifically in this talk, I will talk about three different kinds of structures, namely categorical families, split type categories, and representable maps of presheaves. We will compare these in univalent type theory, and I will not talk about formalization. I just want to mention that everything I'm going to say is formalized in univalent. So specifically, the type theory we work in is a core type theory, say, with, well, the univalence axiom as an important ingredient. The resizing rule that is used in some of the constructions that we are using that are preliminaries for this work, but it's not used for the results of these works. Okay. So there are two different kinds of questions studied in this talk. Namely, if we have different structures on a same underlying category, say C, can we move between these different structures? For instance, can we, from a categories with family structure on a category C, can we get a split type categories structure? It's not necessary to understand what these are for the time being, but so we want to vary the structures, but we also want to vary the underlying categories. So this is the second question. If we have a map of categories, a functor, does a structure transfer along this functor? And as a case that is particularly interesting for us is, does a structure on a category, for instance, a category of family structure, transfer to the same structure on the rest completion of this category? Okay. So this is a summary of the constructions that I will discuss in this talk. I will first discuss this equivalence between split type categories on a fixed category C and categories with families. So here the underlying category doesn't change. I will also discuss the relation between categories with families and representable maps of presheaves. The important difference is that here, this map, it forgets the choice of structure. So here we have a choice of structure, and here we have existence of structure. And we will see that this map is in general, well, it forgets stuff. It is not an equivalence, but if the underlying category is univalent, as is for instance the case with these rest completions here, then this forgetting information can actually be reversed. And a third kind of question that we are going to study is here these horizontal maps where we transfer from a category to its rest completion. Okay. To do this transfer constructions, we introduce a generalization of these notions of categorical families, which we call relative universes. I will give the definition of what that is. And actually, these transfer constructions are very conveniently studied in this generalized setting, as we will see. Okay. So I have prepared a review of univalent categories, but maybe should I do this or should I jump over it?
Oh, I think you should do it.
Okay. Okay. So a category in type theory is usually or is defined to be as given by a type of object, a dependent type, well, a dependent family of sets of arrows, an identity arrow for each object, composition, and axioms postulating identities of arrows. So this is very standard. And then a refinement of that notion is the notion of univalent category, for which this map that we can define for any category is an equivalence for any two objects. So what does this map do? It maps identities between any two objects with two isomorphisms between these two objects. And this map is defined by using the J rule of the identity type. We can pretend that B is A and map it to the, so then reflexivity is mapped to the identity isomorphism. Okay? So we are asking that this map is an equivalence for any A and B, which means that in a univalent category, isomorphic objects are identical. There are as many identities between objects as there are isomorphisms.
So, yeah. Sorry.
Where is it P is? Shouldn't it be that for all A, B, it's an equivalence
So
rather than what's written here?
well, it's not very precise. The map bit to iso AB, index AB is an equivalence.
I see. I don't think this P should be there. The product.
Yes.
Or it should be
Well,
outside of the parentheses.
Yeah, there should be a parenthesis around the function.
you mean around here?
Yeah.
Yes.
What? Right.
No,
I thought
there
there
is
was
E-
one.
I-
I got that. So if I was in the agnostic,
Between the agnel notation and the computation.
so if I was in the agnostic world of ordinary set theory, etc., blah blah blah, I might be thinking about skeletal categories. So you need a word,
Arrow insert
the opposite of skeletal, right? Because this is like they're fat rather than.
Yes, indeed.
I don't know what the right word is, right? But, somehow univalent category is overusing the word univalent, but
Yeah, maybe complete.
yeah.
Well, because in the case of to prove it for the category
It's a
of
special
types,
case, yeah.
it becomes a univalent axiom.
Okay. So examples of univalent categories. Well, the category of sets is univalent is exactly the univalence axiom for sets of a certain. Again, here it should be parameterized by universe, but it isn't. Groups and rings. The functor category CD is univalent if the target category is. Full subcategories of univalent categories are again univalent, and the smallest example I could come up with is this one. So here we have two objects that are isomorphic but not equal. More examples. A preorder is univalent if and only if it is antisymmetric. I can, given a type X that is of level 3, so that is a groupoid, then the category with objects X and humps given by the identity type is univalent. And what will be important later is that if I have a univalent category C here, then limiting cones are unique, not up to isomorphism, but up to identity. So this will be important later. Okay. I mentioned one example of a non-univalent category, so there are a few more. Importantly, we can associate to any category a univalent one in a universal way, which is this rest completion. So this is a kind of quotient given any functor from a category C into a univalent category. This functor factors uniquely via the univalent category RC of C, where this say projection functor here is a weak equivalence.
Is there any way I can picture what RC of C actually looks like?
Yes. So it can be defined as the
It's a hit,
image as a hit. The
Yeah.
objects can be defined as a hit, but maybe more, I like a different way better. You can define RCC as the image of the UNEDA functor.
Oh, I see. Yes.
And then you use the fact that the category of sets is univalent to univalent. So you use all the ingredients that I have mentioned on the previous slide of univalent. Good. That was
You mentioned weak equivalences on the previous slide.
weak equivalences, by
Yeah,
which I
just-
mean
Just
fully
to emphasize.
right. So here I mean fully faithful and essentially subjective, and that is not the same as an equivalence. So I would need an item of choice in general to turn that into an equivalence. Okay. Good. So this is a difficult slide, and maybe the point is not for you to understand this slide if you are not already familiar with that notion. The takeaway message from this slide is that a category with families is a big thing, a bit unwieldy to work with, and I will present a few constructions that help to make this problem smaller. This is the important message. So a category with families is, well, a category equipped with two presheaves, which we think of as types and terms, and a typing map from terms to types, and such that a certain pullback data exists. So anytime I have an arrow into ty, I get data. I get this p, this pi, and this object, and this map. Such that the resulting square here is the pullback. The details are really not very
At this point, the safe thing to say is that, quotes, Jean Benedikt probably thought of this first.
Yes.
Well,
So-
but one has to be careful here. It's not that this thing exists. It's a specification is given of
Yes.
such squares.
Exactly. So
For every a
yes.
for every gamma and a hat, the rest of the square components are specified, chosen.
Okay. A type category, so this is the notion that we want to compare categories with families with, is given by, again, a category C. And then a lot of data, I will not go through it if you don't mind. And we will impose more conditions. We will consider only type categories that are split. Here we ask for the type of, well, types over an object gamma to be a set, and we ask for this completion of squares given by these maps Q to be functorial.
So it wasn't tie a presheaf?
So here in the categories with families, tie is a presheaf, and here it will turn out that tie is also a presheaf, but only for split type categories. Okay.
But it's important, there are interesting examples of non-split ones, and they come up naturally in the study of this, of split things.
Yeah, I think presheaves are not a split type category.
Presheaves are not, well, the comma categories the type of objects of the comma category, C over X.
Mhm.
If I take Cy of X equals objects of C over X. And then I say
So that's
that,
not necessarily a set, is it?
and then, yeah, and then I say I also have a choice of, fixed choice of pullback squares. Then it will give me everything here, but, but that will not be set, and there is no reason why this last condition has to right. I mean, the first condition is not going to hold, and the third condition is probably not going to hold, because your pullbacks are not necessarily functorial in
Okay. So the first goal that I mentioned is to provide an equivalence of types between split type structures on a fixed category and categories with family structures on a fixed category. So what we do to reduce the complexity of this problem a bit is to factor out, so we've already factored out this category C that doesn't change, but we will do more of the same thing, namely we have observed that actually also in this the type categories, this TY thing is actually pre-sheaf, and we also have the both structures come with this object extension structure, as we call it, where for any object gamma and a type A over that object, we have an extended object gamma dot A and the projection morphism. We factor that out, and then
there's no axioms. Yeah. Sorry,
yeah,
just
there's no axioms, exactly. And then we call term structure the remaining part that we need to get a CWF structure, and we call Q-morphism structure what we need in order to, well, complement this to a split type structure. Okay? So now we have reduced the problem to actually a stronger problem, because we want to construct a fiber-wise equivalence for a fixed object extension structure X on a given category C. We want to construct this kind of equivalence between these weird structures. So this is what we do. I will give a diagram on the next slide. What is important here to mention maybe is the following, that going from Q-morphisms to term structures is actually maybe the complicated thing. We have to define this term, the pre-sheaf of terms, which as a standard is defined as the set of sections of the canonical projections. There is no surprise. But if we analyze what is needed to define this equivalence of types, if we go from Q-morphisms from left to right to left, to show that this is inverse, we need function extensionality, and to go from right to right, and show that this is the identity, we need a univalence axiom, because there we compare pre-sheaves two pre-sheaves with each other. Okay, so this is the overall view of the constructions that we do. So these are just trivial reorganizations here to the left, to the right. And the interesting bit is this structure, where that consists of, well, an object extension structure and both a Q-morphism structure and a term structure that are compatible with each other. And actually we show that for each Q-morphism structure there exists exactly one compatible term structure, and for each term structure there exists exactly one compatible Q-morphism structure. Okay, so this is everything I want to say about this equivalence. Are there any questions? So maybe I should mention here that this is one of the advantages of working with types over working with categories, because this decomposition of the problem into fiber-wise problems would not be very easy to work to when categorically.
I can also make one comment that it's very easy to construct an example which shows that the set of Q-morphism structures, if I just do the same definition in set theory, and I get the set of Q-morphism structures on X and the set of term structures on X, and in very elementary examples, it seems that these two sets are totally not bijective. So it's important that that these types are not sets, and so there are actually hidden groupoid structures there, which we recover here without ever talking about this groupoid structure. And it's as groupoids that they're equivalent, but as sets they're not bijective. And there is simple meaning to it. I have the appreciative of terms. When I go to Q-morphisms, I forget about it. And then I recover in U kind of appreciative of terms as sections of the canonical projections. And these two appreciatives are going to be isomorphic. But I can never anymore recover the precise sense from which this term appreciative consisted of. They're lost forever when I just move towards Q-morphisms. The only thing which I recover are their isomorphic copies.
Okay. So the next equivalence that we want to consider, or the next construction, is a transfer along weak equivalences. So if here we have a factor f from C to D, we ask, what do we need to know about this functor to construct a map from, say, CWS structures on C to CWS structures on D? Again, as a special case, as I've already said, the transfer of structure on a category to structure on its rest completion is interesting to us. So to study this question, we consider something called relative universes. It's a generalization of the notion of a universe in a category. So given a category D, a universe in that category is a morphism P, together with a choice of pullback for any map into the codomain of that morphism. Okay. Now a relative universe, a universe relative to a functor J from C to D, is again a morphism in D, and then a choice of pullback where part of the data comes actually from the category C via J.
Yeah, I see. So J might well be the nature embedding.
Exactly. So this rel U of the Yoneda means relative universes on the Yoneda embedding of C, and this is, you have seen, relatively immediately equivalent. Okay. Now, this is a rather cumbersome construction of a transfer of relative universes, of universes relative to J to relative universes on J prime. So there are many variations of this construction with slightly different hypotheses here. The one that is interesting for us is this one, where we ask for this C prime to be a univalent category. And these last conditions will ensure that some choice of pullback is actually a proposition, or a type of pullback is actually a proposition, so that we can make use of these two hypotheses and get and turn them into specified data rather than just a transformation.
And alpha is just a natural transformation.
Sorry, alpha should be an isomorphism.
Oh, I see.
Sorry, mistake. Yeah. So this construction is maybe not interesting in its generality. The important special cases when we, J and J prime are the unetta on C and D respectively. So then we have, if we have a functor f from C to D here, a weak equivalence, we can instantiate the previous instruction as follows. So this functor here from C to D, I should mention if here, I should have D univalent. Is that correct? Then, so
does weak equivalence just mean full faithful and essentially subjective?
as before, yes, fully faithful and essentially subjective. What happens here is that by precomposition we get a contravariant action here. So f circle means precomposition with the opposite functor of f. So this gives a functor from presheaves on D to presheaves on C. And so this is now a fully faithful precomposition with a fully faithful and essentially subjective functor is again fully faithful and essentially subjective. And since it's a functor between two univalent categories, actually it is a real equivalence of categories. And this is, so this right functor here is just the inverse of that. And this instantiation then gives us a transfer of categories with family structures from C to D. As I said, I think I need to assume that D is univalent here. And in particular, I get this transfer of CWF structures on the along the rest completion. Okay. The last point, very quick.
Very good, yeah.
The last point of my talk is to discuss this difference between chosen structure and existing structure. So representable maps of presheaves are basically categories with families, except that we have the pullback data not chosen, but just given like this existing. So we have an obvious forgetful map from CWF structures to representable maps of presheaves on C. And for the inverse, for a map in the other direction, we would in general require the axiom of choice. Some suitable notion of
Again,
choice.
I may just for a second. One can again construct a simple example. That would slow us down, but one can write these examples, very, very simple ones, just kind of combinatorial examples based on group weights BG, where G is a finite group. And usually both terms and types one takes as a constant shift, just 1 point shift. And still there are, it is a representable, well, it's identity, so it is a representable map of presheaves, but there are actually many CWF structures relative to this map of presheaves. And one can consider how the equivalences of the category act on it, and to show that there are actually many non-equivalent, non-isomorphic from the algebraic point of view, CWF structures. So that's a good example where CWF is a big set, while rep is well, I'm choosing 1 point in rep, and I'm looking at the pre-image of this 1 point, and I can show that this pre-image is a big set. It's easy to compute and to show that it's a non-trivial set. So constructing any inverse would require me choosing 1 point in that set, and there is no obvious way of it.
However, if the underlying category C is univalent, then we actually can show that these two types are equivalent. And this is basically just using the fact that on this side, the type we choose from is actually a proposition anyway. Okay, and so that was everything I wanted to say. To summarize, so we have here one example where we consider different structures on the same category. Here, an example of a structure where we forget a choice that we have made, and this is not an equivalence in general, but if the underlying category is univalent, then it is an equivalence. And here, also here we have a transfer of a structure with a chosen structure along a weak equivalence, and this is not an equivalence, but it is an equivalence if we pass to just the existing structure. So, thank you very much.
Well, we certainly have time for questions if there are. I've got one. So you're looking at these various categorical structures for representing type theory, and I can't remember. You're doing this assuming say the CWF or whatever has structure for pi types or sigma types or so on, and you can prove the theorem still goes through presumably if you assume it has.
Okay, so the next step would be to ask whether the structures for pi and so on transfer along these constructions.
But you expect it will. I guess my question is there anything there that might cause difficulty? I'm thinking like universes, for example, would that make it a harder problem?
I have very little intuition for what might happen. I think that like for everything here, I don't expect any problems because this is an equivalence between split type categories and CWS. But when we pass from split type categories to just type categories and compare them to categories with display maps, which are on that end of the spectrum, then I don't know what happens.
But also, I would expect that some of the structures of type theory, at least, do not descend along the to the rest completion.
Here, along this.
Well, along either this or from CWFs to representable ratios. And that would be my kind of feeling, but I also have a kind of a confirmation by there is this paper by Steve Howdy called Natural Models, which he started by defining a natural model as a representable natural transformation, but was forced at some point, I guess, of the reviewing process to say that no, we have to actually choose these things, because some things down the line do not want to work without the choices. I haven't checked which ones don't work, but.
Well, thank you for being so succinct.